I think on the workshop program, I'm TBA. I'm afraid that's because, as with most of the aspects of the organisation of this workshop, I basically left it to Hilary primarily and David. So I tended to that seemed to kind of migrate over to me actually getting around to submitting a talk title. So this is my talk title: Modelling Geophysical Fluid Dynamics with Anisotropic Adaptive Meshes. And yes, I'll just reiterate that I'm a co-organiser of this workshop apparently, but yeah, as David pointed out, I feel a little bit guilty because I did very little work towards it. And so I really should thank my co-organisers for inviting me to give this talk in the opening workshop and for giving the opening talk of the opening workshop. So I'm a member of the Applied Modelling and Computation Group, as well as the Brownfield Institute for Climate Change at Imperial. This is a frivolous little logo for our group, showing adaptive meshing. And for acknowledgements, well, there's probably, I need to be acknowledging more than 50 people here, so rather than listing them all, you'll be able to read them. Look at this webpage here. The people in the room, or should be in the room, who are on the attendee list, include David Ham, one of my colleagues from Imperial, Colin Cotter, John Hill, who's at the back, and I guess also Michael Herzog we're collaborating with on the atmospheric side of this work, although I'm really not going to be talking about anything atmospheric here. And finally, I should acknowledge funding from the UK Research Council, CSRC and NERC. A lot of funding actually from Imperial College itself, and some from industry as well. So what's the plan of my talk? I think I've got plenty of time, so I hope I should be able to get through it all. So I'm going to start off with some motivations, some examples, and some excuses to show some pretty pictures. I'm going to run through briefly the digitalization methods we're using in our finite element framework. I'll then spend some time talking about adaptivity via mesh optimization, talking about the important steps, focusing on mesh anisotropy. I'll go through a multiscale example of tides and renewable energy, and then if I've got time at the end, to talk about balance and high aspect ratios. So some motivation and some CFD/geophysical fluids examples. So one of the things that David didn't mention is that solving the ocean or the atmosphere, you start typically from one side. You're either solving something like a shallow water system and you build in more layers and you move to some 3D geophysical system. We start, which is probably the way we started, on a CFD side. So you look at engineering fluids and then you try and apply those methods to geophysical fluid dynamics. So I'm going to show you some examples in both of these areas. Some more words on the motivation. So what are we interested in? So people involved in this work are interested in challenging problems. Well, we all are, I guess, but what do we mean by challenging? Characterised by multiple scales, complex geometries. So for us, the ocean and its complex geometries is a good example. And coupled multi-physics. So on the CFD side, the sorts of things we're applying these methods to include modelling of boundary layers, turbulence, heat transfer, multi-phase flows, coupled radiation transport, thermal hydraulics, and fluid structure interactions. At the ocean scale, we're thinking about things like linking the estuary to the coastal, to the shelf, and the deep regions or scales. Perhaps explicitly representing or incorporating some small-scale processes within the large scale. And also we're applying these techniques in geodynamics, so things like mantle convection, where you've got resolutions from the boundaries between plates up to global scales. Again, you've got things like boundary layers and heat transfer and very wide temporal scales. So a couple of movies. I'll show you this one first. This is a lab scale simulation of stratified flow over a bump. It's tidal flow, so it reverses. And what you're looking on the top frame here is the entire domain, so there's a boundary condition here forcing flow in and then sucking it out.
What's the fruit number?
What's the fruit number here? Well, I can't remember off the top of my head. We're getting breaking waves. This is the mesh, so you can see the mesh resolving the interface and stratification and the overturning dynamics. This is a 2D slice model. And this is really the gist of this talk, is how can we put resolution where and when we need it. And this is slightly, so that was a pure sort of CFD or CFD with buoyancy example. This is now a sort of more complex example that shows the flexibility of these approaches. So we're using adaptivity to model the interfaces between three materials. So the materials here are the water, the air, and here is a more dense, more viscous fluid that's supposed to represent a landslide. So it's supposed to represent rock in some continuous sense. So this is some work we're looking at in terms of, here it's a sub-aerial, but also submarine landslides and how they generate potentially tsunamis. So I'll come back and I'll mention a little bit more on this later. So our aim is to use the flexibility of unstructured meshes, which David mentioned, and the power of adaptive finite element / control volume methods, which is what you see in these examples. But, and there's a but in capital letters, it's important, these methods typically come with extra computational overheads compared to optimized structured grid type finite difference methods. So the question is, can we offset the extra costs of these sort of adaptive and unstructured mesh-based methods by making maximum use of this flexibility of mesh, so we can put the resolution where and when we need it. So for transient systems, this points to the use of dynamic anisotropic, which I'll come back to, mesh adaptivity. I mean, you don't need anisotropy to still get variable resolution and the dynamic mesh adaptivity, but that's one of the things we do, so I'll come back to that. Our aim is to develop techniques and a flexible modelling framework, so we'll see some of this later on. So by modelling framework and flexibility, I'm talking about the mesh we're using, the digitization type we're using, the physics, and also the coding, the implementation, so we can rapidly test new things. To allow a wide range of coupled industrial and geophysical systems to be simulated. But this is tough. So one of the things that we do in our group is we try and cross-fertilise techniques from different application areas. And well, this is saying something you already know. So these are the sorts of scales, at least in the ocean, that models typically run at. So climate models, 100 kilometres maybe in coarser. We use eddy permitting resolutions of say 30 kilometres. And what you're seeing here, this is just using GMT to pull out the bathymetry and topography in the area around the Straits of Gibraltar at these resolutions. So you can see here, you're really doing a poor job of representing the Straits of Gibraltar, if at all. As you move up to 30 kilometre resolution, we can still see the effect of the grid. You can still see the grid cells here. 10 kilometre, that's also state of the art that people run global models these days. People are pushing that even higher. But the future, 1 kilometre, is where people want to head to for global simulations. If you're running regional simulations, you can go to finer resolutions. The problem is, as you move up here, remember, as you get to this higher and higher horizontal resolution I'm talking about here, you're typically be probably refining your vertical resolution, you're going to be using probably a smaller time step. There's really massive increases in computational costs.
So, Matt, when I see this picture, I have an idea. I wonder if actually this is the kind of idea you're using. So I'm thinking that if I go from the left to the right, the climate model is a Lagrangian coordinate for the eddy permitting, and the eddy permitting is a Lagrangian coordinate for the eddy resolving, and then the future. So, I mean, can you imagine doing it that way? Is that kind of the idea?
Well, our idea is, I mean, one argument is that there's important stuff going on everywhere. If you can argue there's important stuff going on in a finer, a smaller subset of your domain, the question we're asking is, how can you put the resolution where you need it? If you're using a model that doesn't have much flexibility, you don't have the flexibility to put the resolution or the computational power where and when you need it. So I think we're maybe not talking about exactly the same thing. I think what we're talking about is a little bit simpler. It's just saying, where is there interesting stuff going on? Or where is there the potential for interesting stuff going on? Or where do I live and I'm just more interested in that area?
But if you think about multi-scale, that would be this would be one way. Maybe we can talk about that more.
That seems like a good discussion topic. So some more intro on the numerics. So we're using a 3D Navier-Stokes flow solver. Again, that's a little bit different to some people who might be using primitive equation. We're using unstructured mesh adaptivity, so we make topological operations to optimize the size and shape of elements. I'm going to come back to that. The model has been parallelised, but for these sorts of models, quite far. I think for state-of-the-art climate models and ocean atmospheric models, it's maybe not that high. People are pushing up to 100,000 cores and above. But these methods have been tested up to about 10,000 cores and showed to scale well. I think importantly, the model and the framework that I'm presenting is open source, with the aim that it be a community model that people will be able to contribute to the development and the support of this model, and they are starting to do that. And two very important things that I'm not going to talk about, but I can come back and talk offline, are the use of GUIs and other things to mean that people can set up and run models relatively easily, and what's often called QA, quality assurance, or validation verification. How do you know that your model is a model that does lots of things? It's got lots of options for doing the wrong thing and messing things up. It's complicated code. There's a lot of chance once the code is out there in the community and people can in principle contribute to it, there's a lot of scope for people to mess things up in something they're not working on. So this last one is really, really important for us. Yep.
So one of the things that structured mesh models often exploit is that you get the same answer regardless of how many processors you use. Is that something that you can also carry over to unstructured mesh models, or does that become prohibitively burdensome?
I think with the methods we use with an adaptive mesh, you wouldn't. The way we deal with adaptive meshes, you wouldn't get the same answer. I'll talk a little bit later about how we deal with adaptive meshes in parallel. If you're on a fixed mesh, if you had a similar digitalization method, you would expect something similar, with a caveat that most of our methods involve inverting linear systems. So again, then we're in the realm of what the library you use for solving the linear systems would do if it was on a different number of cores, and probably that would not give you the same answer. But if an unstructured mesh with an explicit model, I would expect you to get exactly the same for a finite difference model.
So fully explicit unstructured meshes, we're getting bit reproducibility on different number of processors.
And here's another couple of, again, I'm probably apologies for those people who've seen these before, some other nice examples of some fluid dynamical simulations using adaptive grids. So this is a water collapse problem in a box. Again, you can compare this with lab data to a certain extent. And what you see is the interface between water and air. You can see the mesh, it's not coming out very well here, the mesh on the surface of the box. You can see it's a refinement around the interface between water and air. And this is a simulation that's running on a single core, so it's relatively efficient. And the reason that it is because we're only putting resolution where we need it, and it's moving to follow those, in this case, interfaces. It's another classical example we compare against lab and DNS simulations. Flow past the backward facing step, that's the entire domain there. This is a zoom of the region just around the step. This is just a tracer filter set to 1 on the boundaries, so just for visualization purposes. Next frame down is the multiplicity. And finally, for me, the interesting one is the adaptive mesh. So where are we putting the resolution? There's no slip boundary conditions top and bottom, so initially you see there's extra refinement, but when the problem starts up, so you can see it's refinements resolving the no slip boundary layer. But in the interior, there's nothing basically going on. It's very boring, and so using very coarse resolution. You can see some resolution is starting to build up as instability occurs. And we've got people looking at things like the attachment length and how this interacts with different turbulence models at the moment. So this is a problem that's basically spinning up and then is forced. And if you look at the number of nodes over time, you see this. So we're very efficient here of being able to model this spin-up period efficiently. And then once we've got up to some level where everything's fully spun up, then we're pretty much constant in the number of nodes. Some more CFD motivation, and again, this point that verification and validation is very important. Another test we'll use for this. So this is flow past a sphere, fixed sphere. Half of the domain has been removed here. You can see, you get an impression of the sphere here, or half the sphere here, and this is a zoom in now. So these are the linear facets that make up the initial geometry. So as the mesh is adapting, and extra elements have gone in on the surface here of the sphere, that original faceted sphere remains. This is a zoom now showing you the recirculation and eddies boundary layer separation that you're seeing in the lee of the sphere. And what we can do is we compute the drag coefficient from this sphere at different Reynolds numbers. This is the drag coefficient against the Reynolds numbers ranging from a Reynolds number at 10 to the minus 2, so very sticky, up to 10 to the 4, so quite turbulent. And we can compare, so the dots here are the numerical values of these Reynolds numbers, and the dashed line then is this correlation from lab data. And again, you can see pretty good agreement. And again, the efficiency comes from the fact that we're only putting the resolution, really most of it is just going in to represent the region close to the sphere very well.
Just for clarification, it's a 3D problem, but you're
That's a
showing
3D problem,
2D
yes.
slice through the
Well, it's like a slice, but you can see sort of shadings because we've clipped out some of the elements. So if you sort of move this around, you'll see that sort of be a
So the shading is the actual 3D
yeah.
plane. Okay.
Yeah, so here you can see, because there's a facet that kind of goes like this. And this is a movie, this is a movie of that simulation. So the point here, that's a slice rather than removing elements. You can see it just looks a lot more less attractive when you slice through an unstructured mesh. The point I want to get across here is we're getting very good agreement on the drag coefficient. We're putting all of our resolution basically in this region here, and we weren't really worrying too much about representing the wake. And you can see some mesh effects in the wake, I think. I think you can see that, you can see what's pretty clearly spurious behaviour. That's as the wake moves into regions that haven't been refined. But for this calculation, that was fine. We weren't interested in the wake. We're interested in the drag coefficient, so resolving the flow near the sphere is good enough. The point here is, one of the problems with these multi-scale type methods is you need to know, or you need to have a way of telling the model how to know where to put the resolution. And that's going to be dependent on the sorts of questions or the sorts of numbers you want to extract from your simulation. So here with the drag coefficient, that's a relatively simple quantity that we know we want to resolve the flow close to the sphere well, so that was pretty clear. And actually here, we could force it to put the resolution there by having an artificial field that decayed exponentially away from the sphere and then adapted to that field in addition to the velocities. So the point I was wanting to make was the decision of how you define or how you tell the model where errors are high is a difficult one. I think we're going to hear some talks about that.
The boundary conditions in this problem?
On the series, no slip.
And on the boundaries?
On the boundaries, it's on the far back. This isn't the whole domain. The whole domain's up here. So it's no slip on the sidewalls, and then a uniform inflow at the left, and an outflow boundary condition at the right.
Just an outflow, yeah.
Yeah.
Because I saw that blue bulge at the very beginning go right out of the problem.
Oh yeah. Well, yes. So yeah, that will basically be that eddy would basically decay and leave the domain. Yeah, outflow boundary condition is a bit of a problem. If you get an eddy leaving the domain, that is problematic if part of that eddy is pumping information in. So the way you would normally deal with that is a sponge region just to kill the flow, so it just leaves the domain. Again, here, that boundary is far away from what we're interested in, so that would be fine, typically. So now moving on to some geophysical fluids, we're introducing buoyancy in this example. Again, showing you for the fact that you can test your scheme, verify your scheme, but also check how well the adaptivity is doing by comparing against some quantity that you know. Here the quantity you know is the head speed, so there's a no-slip boundary condition at the bottom. So you can see that forming here, which is the density field, and a free-slip boundary at the top. So the free-slip boundary moves a little bit faster than the no-slip boundary. We can compute the location of the head at the no-slip and the free-slip side, plot that as a function of time, pull out a slope, so that tells us the velocity that the no-slip and the free-slip the gravity current at the no-slip and the free-slip is moving. We plot that head speed as a function of number of nodes using a fixed mesh. So this is now using a fixed uniform mesh. So we'll just chop the domain up into a structured mesh, and then chop each of those squares up into triangles, for example. That's one way we can get a structured, or a pretty uniform mesh. And you can see we do see convergence, and this does represent a good agreement to both lab and DNS data for the head speed. And this is the no-slip head speed, I think. So the point with the adaptive simulation that you see here is that's the head speed that we get with the adaptive simulation. So you can see it's a pretty good agreement. But it's using about 2 orders of magnitude fewer nodes. So I said in an earlier slide, well, the problem with these methods is they're more expensive, maybe by an order of magnitude.
Why the vertical lines error or something?
So because this isn't perfectly linear, we fit.
No, I mean on the blue, the vertical lines.
Yes. So because these lines aren't perfectly linear, we fit a
Yep.
linear line. That's what this point is. And these are, if we sort of take smaller chunks of that line, what the variability is. And that's just showing, for example, as an eddy is shed, the nose might periodically just like slow down a little or speed up. And then these bars here are showing that's the average number of nodes in the adaptive simulation. That's the maximum number of nodes that was used.
I think that's the speed of the lower front, the no-slip one, right? The blue.
Yeah, well, this is both of them, but yeah, then this is
Yeah.
just for the. If I recall correctly, that's just for the no slip.
And what's the speed of the upper one, the free slip one? Looks like it's going to be above a half by a fair amount.
No, there's a limit of a half actually.
Well,
So
supposed to, but,
so if I can find that information in a paper. It might well be. I think that's 0.42. The free slip might be something like 0.45 or 0.46, but I can look those numbers up for you. Or it's possible
Would
that I
it
put
be in the
it.
ratio of those slopes?
Yes, it would be. Yes.
So it would be 5/4,
In that case, maybe I'm wrong. Maybe this
25%.
is
That'll
the,
get it over 0.5.
In that case, it's probably this is the free slip then.
No, because that only is getting up to 0.42, which would be too slow.
I get maybe a coffee. This is in a paper, so I can show you. I can show you the results that are in the paper, and they are definitely below a half. So the next thing I want to show you is the use of adaptivity to minimize spurious mixing. So this is an example of one of those Kelvin-Helmholtz billows rolling up, and the use of adaptivity again to resolve that interface between the lighter and the denser fluid. The nice thing here is that we get, multiple roll-ups of these this density filament, if you like. It's obviously helping us minimize any spurious mixing we're getting from numerical dissipation. If we plot the background potential energy or the relative change in background potential energy, this is a measure of how much mixing is going on in the system. So there's a lot of information on here. So these grey lines are 3 different fixed meshes at different resolutions. You can see the amount of mixing is reducing as we're refining the resolution. This is telling us that as we refine the mesh, there's less and less spurious numerical dissipation coming from the advection scheme, which is what we hope we expect. Adapt 40, this means we're going to adapt the mesh every 40 times depths. That's the average number of nodes in that calculation, and this is what the background potential energy is doing in that case. So there's more mixing, there's more spurious mixing. That could come partly from the fact that you've maybe got a coarser mesh in places, and so that's going to feed in through the advection method to more spurious mixing. It could potentially also come from the fact that you have to interpolate the solution fields from one mesh to the next, which could introduce extra dissipation. I think in this case it's mainly coming from the advection method, and the reason we can conclude that is that we've also run the same adaptive simulation, but adapting with 10 times this rather than 40. Okay, now this is an issue because the cost of an adapt is non-trivial, so you want to do it as little as often, as little as you can. But the problem is, if you adapt too infrequently, you put the mesh where the interface is now, it's then going to advect forward. You might advect into a region where you've got a coarser mesh. It's going to interact then with the dissipation that you get from the mixing from the advection scheme, and that's going to spuriously spread out the interface. So I've got a picture of that actually, but you do see that. So the jump from the blue to red is just for adapting more often. In metric advection, so the dashed blue is exactly the same as this adapting every 40 time steps, but we're now advecting the metric. What this means is that our metric is telling us where we want the resolution. Metric advection means that what we do is we advect it forward for potentially half of that 40 time step period and say, or actually what we do is we advect it forward for that entire 40 time step period and then take an average of the metric over that period and adapt the mesh based on that wider area. Is there a
So
question?
remind me, the elements aren't Lagrangian, the key?
No,
That's right.
not
So,
here.
so that's why increasing the frequency is making them less
Yeah.
diffusive.
So there's a jump from this. We've got a fixed mesh here. We're solving the physics for a set number of time steps. In this example, a set number of time steps. The dynamics change, and then we re-evaluate an error metric, recompute a new mesh, and then interpolate from one to the next and carry on. So for some of these problems where you've got Lagrangian features advecting around, some kind of Lagrangian component of mesh movement would be good. I know Chris is going to talk about this tomorrow, Friday. So the ideal would be some kind of combination of mesh movement, where that's going to do a good thing, and then this sort of what we call mesh optimization. For example, to change the total number of nodes. Mesh movement doesn't change the number of nodes, and mesh movement can also lead to tangling.
Have you done the adapting every time step?
Well, you could just change the number 40 to 10. You could change that to 1.
Right.
That's probably pushing it too far. Okay, 10 is probably, for most of the things we do, between 10 and 20 is a reasonable number for most of the simulations we do. So 40 is artificially large. It's artificially large to make a point. 1, the cost of an adapt is about between 1 to 2 time steps equivalent cost. Okay, so if you're adapting every 10 time steps, that's not a massive extra cost.
No, yeah. And
If you're adapting every
from the
time
point of view
step.
of cost, but from the point of view of this curve, are you sure that it keeps getting shallower?
We haven't tested that, no. So what you might expect is at some sweet spot, which might be 10 or it might be 5, you might minimise this effect, but then you start to do too much mesh-to-mesh interpolation that could introduce its own dissipation, so you might even go back up again.
The right answer is 0 here for the entire simulation? Or what
See,
is
there's a
the
little
right
bit of
answer?
background diffusivity here, so
Which of these is closest to the right answer?
this one. Okay, so I think I've made the point here. So metric advection is the thing that pushes the mesh forward, so you're advecting into a region that you know the interface is going to move. So this is like a poor man's version of an a posteriori type error measure, where you actually look at where you're going to need the resolution in the future. But the point here is, if you look here, this fixed mesh had 1.2 million nodes. This fixed mesh had 5.1 million nodes. This adaptive simulation, where we've used metric advection and we've adapted every 10 time steps, is using, well, here nearly 2 orders of magnitude fewer nodes. So this is again getting us potentially this increase or decrease in the degrees of freedom we need that's going to offset the extra costs associated with carrying around an unstructured mesh, doing all your discretization operations, everything on it, as well as the mechanism of adapting the mesh.
Matthew, how does they compare in terms of actual walk time between your? So
I've got some numbers later that's going to compare some walk times. In the paper this comes from, actually, well, there's a 2011 paper that was looking at the head speed, so the previous plot. There are some timings in that paper, so again, I can point you in the direction of the timings from that paper. Anecdotally, what I'll tell you is that Hannah Easter, who was doing this work, she would typically run these sorts of simulations on a particular cluster, where she would use a large amount of the cluster. The adaptive run she would use on a much smaller cluster, where she would use a smaller number. So the run times were typically the same, but she was using maybe 256 cores for this calculation, and maybe, I don't know, 16 or 32 for that calculation.
But it's a very hard comparison to make, because that fixed mesh computation is still too slow, because it's been run in ICOM. And if you wrote something that could only do structured fixed meshes, it would go faster than ICOM. So there's a very tricky trade-off as to what you measure against.
Very loosely, so if we say that an unstructured mesh model is 1 order of magnitude more expensive than a structured mesh code, which is a ballpark correct figure based on how it accesses memory and things like that. So to offset that extra 1 order of magnitude, we need to use, let's say, 1 order of magnitude fewer nodes to get the same answer. So anywhere where I show you I'm saving 50% of the nodes, that's not good enough. I need to be saving at least 1 order of magnitude. So I'm showing you this here that I'm saving more than 1 order of magnitude. So that's potentially promising.
You just mentioned that if you do adaptivity each step, it's gonna be like double the cost or something. In the adaptivities, is the adaptivity itself or the load balancing the expensive?
No, the adapt itself. I'll come to the load balancing. The load balance is actually pretty low.
I was just going to say real quick, I think the factor of 10 might be true for a unstructured mesh that's doing adaptivity, but for an unstructured mesh that isn't adaptive in time, we're less than a factor of 2. So I just, for those in the audience that, because a factor of 10 is kind of pervaded the community.
That number has tended to come from the CFD community. I agree. And if you're within a factor of 2, then that's good news, and you've also been very clever.
Actually, no, we haven't been clever yet. That's why I think so.
I mean, clever
Is
yet.
that a 3D structured in the vertical code then?
No, that's a 2D unstructured, structured in the, so it's an ocean GCM.
So it's structured in the vertical.
Structured in the vertical.
Yeah, but that gets you most of the way back.
So maybe that's why we haven't needed to be clever yet. But that's who we compare it to, right? It's a global ocean model compared to a structured global ocean model.
That's a structured ocean model where the fastest varying is in the vertical.
Exactly.
Whereas the way that it's traditionally been done is you have it fastest varying in the horizontal because large parts of the dynamical core and the barotropic solver specifically.
Yeah, so I guess maybe we were a little clever. Yeah.
Okay, so you.
Right. Yeah.
That's good news, right? Because that would mean, well, I'm going to show you some results later where we do things a little bit differently from the horizontal and vertical. So that would work very well if that's a different coding paradigm that gets you that.
I think the order of magnitude thing comes from the assumption that you have an indirect addressing operation at the innermost loop.
Right.
And you've got your indirect addressing operation 1 loop out.
Exactly.
And that makes a huge difference.
Yes.
When you say factor of 10, is that a comparison? Have you done a comparison of this code with the structured code, or are you just quoting the CFD?
Yeah, I'm just quoting the CFD. I mean, it's a little bit. It's quite difficult to, because we're solving typically non-Boussinesque full Navier-Stokes. So it's a little bit hard then to compare against an ocean model that's running hydrostatic. You can do. We've done it to a certain degree, comparing with MIT GCM, but then it's like how many cores are you running it on, how well does it scale? So it's a little bit difficult. I think at the moment we'd be happy if we were a factor of 10, right? But that's factoring in the fact that we're running on different machines, different core counts, hydrostatic versus non-hydrostatic. And I guess the other thing, and then for sort of CFD benchmark problems, there aren't that many sort of just, you could write your own final difference Navier-Stokes solver, but then it's not really a fair comparison. So I would say we have done some anecdotal comparisons against some commercial CFD packages, and they're less more difficult. You don't get access to the source code, but then I think we're fairly consistent with those that we've seen so far. Yeah.
I'm going to bring you back to your slide, which you're going to regret leaving on the screen for so long. So what I'm seeing at the end there, you're seeing this kind of geometric growth of.
Well, that's just where it hits the end wall.
But you also have a growth of structure because of a cascade that's growing, right? In the experiment you showed, it was scales are growing in time. Right. There was no structure, and then you get limitation and so on. If you were doing an equilibrium situation where there was a steady state spectrum, how would you then be picking up the raw numerics and not your ability to adapt, because you're going to fix the number of nodes and there's going to be a continuous smoothing because you've got a limited resolution now. And that's probably the more relevant measure, because in climate models we are trying to do equilibrated problems. So just as a comment, those sort of idealized tests, they tell you a lot about some of the methods, but you've got, I think the thing we're looking for is what's going to happen when you've got a steady forcing in a steady state.
Yeah, it depends what sort of, either a climate model versus a process model versus someone's dealing at the sort of the coastal scales or coastal engineering scales even. So it very much depends on what. And I think people have said for a long time that there's no one model that can do everything better than all the others, right? It's been known for a long time that even running the same problem in different parts of the domain, different models with very different numerics are going to be better or worse. So I think that situation is going to be is going to be the norm for forever in principle. But yeah, you're right. Well, I think I'll move on. Really, I think this gives you the point. So I'm going to go through. I might go through the discretization options quite quickly to get onto some of the details of the numerics. So how does our model deal with the discretization? So I'm going to show you the time loop. So this is one time step. Within that, we're solving the Navier-Stokes equations. We do a nonlinear iteration. We assemble and solve whatever scalar equations we're dealing with. So here I'm just using some of the temperature, salinity, internal energy, epsilon if you've got some kind of Rand's model, biology or sediment. Evaluate densities, via equation of state, assemble and solve a couple momentum pressure system. So the different colours are basically libraries where we go off and pull out code from different libraries and glue them together to make this thing work. So you can glue them together in a different way, and you get a shallow water solver or something else. The things that are underlined are things that we've developed in-house, and the other things are libraries that are available open source online. So I don't really need to say much here other than we do some time steps, we iterate the nonlinearity, we solve for the scalars and the pressures and the momentum, and then we adapt the mesh if appropriate. So if appropriate, what does that mean? Well, it might depend on what the simulated time is, the number of time steps, what the mesh quality looks like, and then we do these steps which I'll come back to. What are our discretization options? So within this flexible framework, we've implemented a lot of options, and that's proven to be quite critical in us being able to solve different problems. So the simplest, if you're in the finite element world, is probably the continuous Galerkin. So using continuous basis functions. This is a basis function focused at this point A that's piecewise linear. That's fairly simple actually, there's not much you can do with that. The one thing you can do is add some kind of stabilization scheme. Stabilization schemes for infection that you typically add for continuous Galerkin are some kind of streamlined or streamlined wind Petrov Galerkin stabilization, which to be honest are pretty dissipative. They don't work that well. They're very robust, but they tend to overmix. Discontinuous methods have for a long time been known to be very good for infection-dominated problems. The flavour we use, so this is an example of a discontinuous basis function now. So the points here are the degrees of freedom in a P1DG function space if you're discretizing your equations. If you look at the number of points here, there's a lot more points or degrees of freedom compared to the CG space. So jumping just from CG to DG, just on the same mesh, not increasing the order, changes the number of degrees of freedom that you've got by a lot, which also needs to be factored in when you're thinking about how accurate these methods are and how efficient they are. So with the DG methods, we've got more options, but the options we tend to use are to upwind the effective flux, to use a compact DG diffusive flux, and then on top of that, potentially options for how we might add some stabilization, so typically based on a slope limiter. And then also, so the CG and the DG are valuable for the tracers, and also, come on the next slide, how we deal with pressure and momentum. The control volume methods mainly are used for affection. If you're interested in preserving sharp interfaces, CV methods, which are very, very similar to finite volume methods, are very powerful. And just like in the finite volume world, you can flux limit between some low and high order flux in a clever way to try and preserve sharp interfaces. So this is all fairly classic stuff. And then the CV, in fact, the reason we call it a control volume rather than finite volume is that it's a control volume on the dual mesh. Okay, so we might be dealing with some of our solution fields focused at the nodes of the elements, and then the control volume space would typically be formed by this dual cell surrounding it.
So Matthew, I'm curious about the statement. So flux limited between, it says high order flux obtained with finite element interpolation. So is this a way around the old adage that you can't do high order unstructured finite volume? So I remember that being something we were told you can do unstructured and high order without massive expense or some sort of approximation. But if you have an unstructured mesh, it's just hard to do high order fluxes with a wide stencil.
I think
You
this
don't
is
have
just...
a wide stencil and a finite element.
So that's the way around it, because you're using the finite element.
Yeah,
So in finite difference and finite volume land, when you want to go to higher order, what you do is your stencil gets bigger compared with the topology. Whereas in finite element land, when you go to higher order, you effectively are refining within an element, and so it's a different kettle of fish. So
Compact
yes, it's
versus not
easier.
compact pencils.
Yeah.
Yeah, so we've got the solution field that's disclosed using CV will then have values then at the nodes. We can just fit our piecewise linear, for example, through those values, and that's a way using finite element space that we can get the high order flux. So the final thing then, so the previous slide was really how we discretize each individual equation. How do we deal with the coupled pressure momentum system? So this is the so-called element choice, which is the finite element analog of staggering in finite difference world. So again, we've implemented actually need to use a whole bunch of different options depending on what application we're using. So for most engineering fluids, P1, so using a piecewise linear continuous for pressure and for momentum, while not being LBV stable, actually works well in practice. Sort of the spurious modes that do exist don't typically get excited very much. So that tends to work fairly well. And actually a lot of the results I've shown you have all been using that P1 element type. So again, some people might object to this, but very loosely LBV stability is the presence of checkerboard-like modes. This is very loosely the case, is that one should have a larger space to represent velocity than pressure, as pressure can be thought of as a constraint. But the accurate representation of either geostrophic or hydrostatic balance, where you want a derivative of pressure to balance, for example, the velocity or a density, actually means it's telling you, in some sense, the opposite. You want the derivative of pressure to represent a velocity. That means pressure itself should be one order higher in principle. So we actually tackle this with two approaches. One is our earlier approach, which some of the results I'll show you use, where we work out a more accurate balance pressure. So we split pressure into the pressure that's preserving our div-free constraints, which might be P1 or what have you, and then we solve for a separate balance pressure where we've got freedom to choose that to be P2 or P3. And if I've got time, which I probably won't, I'll come back to that in a slide later on. Our more recent approach is to use a more exotic combination of CG and DG spaces, i.e. we represent velocity in a piecewise linear but discontinuous function space, and P is then a piecewise quadratic continuous. And the reason that's quite nice is that if you differentiate P, P2, it's going to live in P1 dg. So this is this so-called P1 dg P2 element choice that Colin Cotter, who should be, I'm not sure he's here, and David Ham and others have worked on, and it works well on these large systems. I think I might skip this in the interest of time. This is just telling you that how we deal with velocity and pressure is a pretty standard pressure correction based method. It's done in the discrete sense, in that we are forming our pressure Poisson equation is actually formed in the discrete space. So this is a finite element representation of a Poisson operator. And then
although in P1 DGP2 that's equivalent to doing it in the continuous space. Part of the magic of P1 DGP2.
So I'm going to skip the details other than saying this pressure correction, there are some extra terms, and these extra terms are actually quite interesting. So how we deal with the free surface, or inundation, or wet, i.e. wetting and drying, is basically dealt with in those other terms. How we deal with compressibility, so I mentioned earlier the stuff that we're doing in atmospheric flows, is again dealt with through the extra terms in the correction and the pressure correction. And also there's an extra term if we're using the balanced pressure decomposition I mentioned on the previous slide. But I think in the interest of time, I'll move on to talk about adaptive mesh methods and anisotropy. So there are different methods of doing mesh adaptivity. To be clear, I tend to first say that we do mesh optimization rather than adaptivity. Adaptivity might mean that you're doing some kind of hierarchical splitting of elements, or it might mean that you throw away your complete mesh and you just regenerate a mesh. We do mesh optimization, which is where we start from the mesh you've already got. So obviously we need to initiate that initially with some kind of mesh generation. But then we have a method for looking at the size and shape of elements and then do some operations. So the first operation is an edge split. We look at an edge, we make a decision that it's too long, we just split it. It's quite simple. That obviously changes the edge lengths and gives you more nodes and more elements. You see you've got one more node, but you've got a lot more elements. The opposite operation is an edge collapse. So if we identify an edge that's too big, based on our measure of what is too big and too small means, we can collapse it. That's interesting enough. I'm more interested in these operations. These are interesting because they don't actually change the number of nodes at all. Okay. This one changes the number of elements, but this one doesn't change the number of elements. This is swapping a face with an edge, or vice versa. This one here is identifying an edge and swapping it with other edges. So the interesting thing here is this is changing the alignment of the elements. This is how you can get long, thin elements. A combination of previous operations and these ones are how you can get extremely long, thin elements, which you wouldn't get if you had some kind of hierarchical approach, for example. And finally, a little bit of mesh smoothing helps. I think not massively. It basically comes in at the end to tidy up some of the elements that you've got from the previous operations. So in combination, the above operations alter the resolution and the alignment of the mesh, using a mesh closer to optimal, however you define that in terms of required edge lengths. So there's a whole, from the 90s and the 2000s, there's a whole bunch of people that are doing these mesh optimization approaches in 2D and 3D. And if anyone's interested, we're developing a new library that's hybrid OpenMP MPI. So if anyone's interested, ask me and I can put you in the direction of some references. I said I'd tell you how we parallelize this. So what we do, if we're running this on multiple processors, we have halo regions that define the overlap between what's owned by one element, but one processing core, and what's owned by the next. The yellow here is that overlap regions. This is the region where we would be communicating between subdomains. These areas over here, this will be one subdomain, this will be another subdomain. What we do is we lock the halo elements and then we only adapt within each subdomain. So each processing core runs our adaptivity library on the elements it owns that aren't within the halo. What that means is, after you've finished, is all the elements inside your subdomain are optimized, but the halo region isn't. But also, we need to balance the load. It might be that this region over here, lots and lots of nodes have gone in, and the one next door, lots and lots of nodes have been taken out. That's going to lead to a load imbalance. It's going to give you really poor parallel performance. So we know we need to change these the locations of these halos anyway. So we perform the load balancing and the data migration at the same time. So we're looking in this load balancing to optimize the amount of work each processor does. At the moment, I mean, you can improve your model for how much work each processor is doing. At the moment, it's basically based on the number of nodes, which isn't necessarily a great correspondence to how much work it's going to do, but that's what we do at the moment. We want to optimize the amount of work on each process, subject to minimizing the size of the halo. You want to minimize how much communication you're doing between processes. So what we do is we weight the edges in terms of the element quality, which you'll see in a little while. What this does is it dissuades the new partition from going through any unoptimized elements. So here you can see it. So one operation of this load balancing would perturb the halo region. Okay, so these three previously unoptimized regions are now free to be optimized. These slightly darker yellows are now regions that have not yet been optimized. So what we do is we iterate on this a few times, and by iterating, you'll eventually have something that's been adapted everywhere, and you balance the loads. And there was a question earlier about the migration costs, I think, or just the load balancing costs. And actually, they come out. So we've done some benchmarking on this. This is an overflow type problem. This is a dome test case, if people are familiar with that. And the cost of the data migration and this whole load balancing step is actually pretty minimal. You can look at, I can point you in the direction of the actual numbers. So how do we describe the edge lengths? So the previous slides were saying, the model somehow knew what was a big edge and what was a small edge. It's actually very simple. It's probably the simplest thing you could do to have an anisotropic measure. So it's motivated by interpolation error theory. So assume you've got some scalar u over some element e. That's the linear interpolant, or the exact solution onto the mesh. It's the error between the full continuous solution and the linear interpolant in the infinity norm can be written like this. And this is just a high order extension of Taylor's theorem, where your second order term would be the error if you were using linear interpolation. And what this is mapped. So this is an order 1 constant that's independent of the mesh. So later on we're just going to ignore it. Then it's a max over all the locations x that are in this element we're considering, and also max over all vectors v that live inside the element. Then v transpose the absolute value of the Hessian times v. So the Hessian here is a matrix of second derivatives. If we diagonalize this, these are the eigenvectors, these are the eigenvalues, the absolute value of the Hessian is just defined as this diagonalization where we replace the eigenvalues with absolute value. And that's just telling you you're interested in the magnitude of the curvatures, not the actual sign of the curvatures. So for practical use, we drop this constant, it's mesh independent, so it doesn't matter. We replace these vectors with element edges, and we assume that we have an edge or element centered H. That removes basically the X, this maps operator here. So what I've said here is this now really means it's not really an error measure in any real sense. It's an error indicator. It's giving you an impression of where things are changing rapidly. So it's giving you an indication of what locations and in what directions the second derivative, the curvature of the solution is high. So equidistribution of a user-defined error. So the user now specifies on field U, I want to attain an error of epsilon across all of the elements. What does this mean? So this means that we want this epsilon to equal this thing where we've managed to lose the math operators. And I want this to be true for all edge lengths V in the mesh. Now this is equivalent if I define M to be this Hessian divided by that user-defined tolerance. It's basically saying that in this metric space defined by this M, I want every edge length to be 1. So that's what we do. We go through, and in those previous slides where I was saying, is this edge length too big or too small? We decide that based on this metric. So we defined a metric space effectively where equidistribution of the errors that the user specified in the physical space, that's the space where we're looking at our adaptive meshes, is equivalent to having a mesh in the metric space of unit equilateral triangles or tetrahedra. So now you've moved your problem of adaptivity to actually either generating a mesh or optimizing a mesh in metric space that's basically uniform. I'm going to hurry up a little bit. So to formulate this optimization problem, we define a functional over every element. R's are the edge lengths of the element in question. The rho is the insphere radius. Alpha is the insphere radius of an equilateral tetrahedra. So basically these two terms would be 0 for a perfect TEP. We evaluate the lengths R and the insphere radius with respect to the metric M. And then we minimize this functional by applying the operations that you saw on the previous slides multiple times. And, well, I'll skip some of the details, but briefly, when you have multiple metrics, which you would typically have because you would have multiple fields that you want to adapt to, we then superimpose these metrics. So we find basically the biggest representation of the edge lengths that satisfies all of the individual constraints for each of the solution fields. 2D, I've showed you 2D problems versus 3D. In 2D, we make use of another library which you can get online, which is basically the same philosophy, but the functional is a little bit different. And we can talk about that at coffee if people are interested. I think in the interest of actually showing you some later results, I'll skip the conservative interpolation, even though it's very interesting. One of the big issues on adapting meshes from one, interpolating solution fields from one mesh to the next as you're adapting, is that you don't want to introduce any errors, or too many errors, which here you can see we're adapting a top hat function, which is a difficult thing to represent, across 100 arbitrary meshes. So they're not adapted in any sense to the top hat function. You can see it's not conservative, it's very distributive, errors are high, and this is an approach that is more accurate, it's conservative.
Are these like linear elements or quadratic or?
Linear, there were linear elements here. So again, I can come back and tell you the details, or you can look at these papers by Farrell and Madison, which I can point you to, but I'm going to skip to talk a little bit about anisotropy. So this is a test problem where from a Western boundary current, so this is a steady elliptic problem you can solve for a string function, which gives you Western intensification. The nice thing about this problem is there's an analytical solution, so we can solve it using different meshes and compute the errors. So this line here is just showing you what second order convergence is. This is now using the fluidity framework using a uniform mesh. So, well, we're getting the second order convergence we expect with P1 elements, so that's good. If we turn on mesh optimization, we adapt to Western boundary current. This is now how error converges with a number of nodes. So you can see there's a little under an order of magnitude saving going from the uniform mesh to this adaptive mesh. But the reason I'm showing you this slide is because this adaptive mesh has been limited to the elements. The maximum anisotropy these elements can have is 2. Right? So the maximum longest edge length to the smallest distance across the cell can be 2. And I think it goes 2, 4, 6, 8, 2, 4, 8, 16, 32, I think. 2, 5, yeah. So that's limiting it to 2. This one here is limiting it to 32, I think. So here you can see that we're allowing the optimization algorithm to produce long-term elements. And we know that the solution field is changing a lot in this direction. So part puts in resolution to resolve that boundary layer. But in this direction, the flow's intense, but it's not changing by very much. We can get away with longer elements. That gives us now, going from isotropic refinement to anisotropic refinement, nearly another order of magnitude. So this is getting across those boundary layers of things with high anisotropy are important. Having anisotropic cells is potentially interesting. This is an example of advecting a tracer field using the velocity field that comes from this string function. Now, as you're advecting this Gaussian through the Western boundary, it obviously gets stretched. That makes it more difficult for the advection scheme. And I don't have time to talk about the details, but comparing uniform with adaptive, comparing either the error in the solution or just maximum value, a simpler metric, again we're showing improved results using order of magnitude fewer nodes in general. But I'm going to skip it to get onto some more interesting results. This is again an old movie that many of you have seen, but I think it's still nice because, well, 2 reasons. One is on the left you can see that, again, very, very high anisotropy that's been used to resolve the boundary layers. And the other reason I like this is because you can get an impression of what the dynamics are doing just by looking at the mesh, which I think is
Is there a limit to how anisotropy can be?
Not in principle, no. I mean, I don't think I've seen. I think in the sorts of things that we don't typically measure it generally, but probably an anisotropy of 100 or so is probably we've not run things that are so extreme, but you could artificially come up with problems that are so extreme that in principle there's no limit. But that is, for our day-to-day work, that's pretty extreme.
In the fixed mesh world, if you have meshes that adapt, your time step is limited by the smallest piece. Here, is there an analog that when you have exceedingly small scales, you have to do large numbers of iterations to converge or something?
That's a good question. I always forget to make this point when the slides come up, so thanks for asking that. So we do also have something similar to a correct number type limit on time step. We're semi-implicit, so we can break it, but still it's there. You can't push it too far. The nice thing here in these sorts of problems is the higher velocities are typically in this direction. So what you need to think about is how fast is information travelling across a cell. And if you're talking about advective information, at least, then the advection in this direction is high, but then your delta x in this direction is high. Right, so the fact that you've got this anisotropy means that we can get away with a bigger time step here than we could if we were isotropic, and so that size element meant that we had to have that size element in that direction. We would then be forced, if our time step limitation was dominated by advective processes, to be having to use a smaller time step.
The fact that waves, which could go
That's
transversely, are linear.
That's a different question.
Well, but they're a linear solution, or nearly linear. So that's something where your implicit solver takes care of that, right?
Yeah. Yes. So for free surface waves, for example, we typically can break a wave speed like a current number. If we don't mind completely damping out the waves, we can run with current numbers of orders of hundreds here. The question is whether or not you care about damping these waves or not. So I'm going to quickly skip through one multiscale example and then move on to. I'll tell you something a little bit. The reason I'm showing this is I think it's quite nice, and it's some of the work we've been doing, or I've been doing quite recently. So tidal stuff is maybe not that interesting, but some of the way that you make it more interesting is looking at paleo tides. So we've had some fun looking at some interesting geometries. So this is a lower Jurassic, so going back nearly 200 million years. We've got automated methods of generating meshes in these regions and looking at tides. Validation of the tides around the UK. If anyone's particularly interested in this, I can talk offline about this. Comparing with tide gauge data, again showing reasonable agreement. We've got several summer research students working on actually this, plotting where we're doing well and where we're doing not so well. It tends to be where we're doing not so well is actually where we're not resolving the problem into harbours or into rivers. That's quite good. This is one of our early multi-scale examples where we were resolving tides in the Atlantic down resolutions where you can see here, and resolutions about 2 orders of magnitude higher in the exchange between the North Sea and the Baltic. But that's not that impressive now, because we've more recently been doing some work looking at marine renewables around the Orkneys. This is an example of a multi-scale mesh. So we've got one scale here, which is far field 20 kilometres. So these resolutions are about 20 kilometre cells. The coastline is represented with a higher resolution, roughly 2 kilometres. This is a PDF of what the edge sizes are in this simulation. The region around the Orkneys is about 200 metre resolution, so that's this sort of resolution here, is about 200 metres. And the region in this particular part of the Orkneys, which is just there, that dot there is that island, is between 2 and 5 metres. So going from the smallest edge length, which is in here, up to here is a 5 order of magnitude variation, which I think is really pushing the multi-scale. And you need that if you're going to, in some sense, here it's still parameterised, but try and represent individual turbines in a potential tidal turbine array. This is a movie of the dynamics. So another thing is having this multi-scale frame that actually runs robustly in reasonable times. This is the Pentland Firth, And if you look at the size of the velocities, it's a potentially interesting region for renewable energy because, well, the tidal currents get up quite high and it's fairly shallow, so it's potentially a good area for people to put tidal turbines in. And you can see some reasonably interesting structures forming. So while we haven't used dynamic adaptivity on this application yet, that's something that would be of interest to us. And in other parts of the Orkneys, there's other areas people are interested in. So if anyone's heard of the European Marine Energy Centre, that has a site up here. So there's lots of tide gauge data, ADCP data for doing comparisons, and several other models, both CFD and sort of unstructured coastal models have done case studies around this area. So that's work we're doing, hoping to do in the very near future. And why are we doing this? Well, in the long run, what we're looking to do is embed the turbines that you saw in that previous 2 slides ago were represented by increased little patches of increased bottom drag. And what we're aiming to do is, while still parameterized, improved parameterizations of turbines in a 3D mesh. And I'm going to have to really skip my last few slides to even attempt to finish on time. So this is now a 3D problem with buoyancy and rotation. It's only about a 10:1 aspect ratio, so basically all of our element choices and 3D adaptivity works okay. One caveat is this is P1, P1, but you need to use the balance pressure solver, otherwise this would be too noisy. It's only an aspect ratio of 10:1. This is now an aspect ratio of 1,000:1. It's a simpler problem where we've got this, so it's taken from this paper here. There's some denser water in the middle, which will restratify, or should restratify. If you use a fully unstructured mesh, unstructured in the vertical, you get a lot of spurious noise, no matter what element choice you use. If you use layers in the vertical, or you use columns, but with columns you don't necessarily need to be layered if you've got an unstructured mesh. If you look here, there's a finer mesh in the vertical here than there is here, so you've still got flexibility in changing the number of layers.
What do you mean by layered?
What do I mean by layered? I mean every column has the same number of nodes.
So that kind of Z-coordinate type thing.
Yeah, but yeah, effectively. The difference between here and here is really, I mean that you can have a different DZ in different X and Y locations. So we can run some spin down like experiments. The number of nodes, Ks, this is quite an easy problem. We compare it against other models and it seems to be working fine. So this is, remember, a 1,000:1 aspect ratio. I'll show that movie again. You can see that it's adapting, it's coarsening the mesh both in the horizontal and the vertical. So what's the problem? Well, if you look at the vertical momentum equation and look at hydrostatic balance, and if you've got a fully unstructured mesh in the horizontal and the vertical, you can think, well, so this is in the vertical now. If we assume that we have a linear pressure, which we do in the P1, P1 type simulations, so the truncation error in the horizontal part of the pressure, again, sort of Taylor theory type analysis, will be the second derivative of P times your delta X mesh spacing squared. What error is that sort of truncation error going to feed into your vertical pressure gradient? Well, let's pretend we've just differentiating the vertical, then we're going to divide through by delta Z. So this is a back of the envelope calculation. You can approximate this roughly using geostrophy as roughly something like this, which, if we relate U to W through the aspect ratio, looks something like this. So this is very hand waving. What this is supposed to show is that this is an estimate of what the error in the balance here is going to be, just in the truncation errors of using an unstructured P1 mesh. We want any error in this balance to be much smaller than this, otherwise we're just going to get completely polluted. I know, I can do that. I have had some questions during, so I'm not. So anyway, we want this quantity to be small in comparison to W. So, and again, in a hand waving sense, as the aspect ratio goes up, if we assume for a second that this quantity here is fixed, this is telling us that we've got some kind of constraint on what the delta X needs to be. So this is a little bit hand waving, I'm afraid, but we're currently working to understand this constraint and what it means. But at the moment what it means is that we're fixed at high aspect ratios to do what we call 2+1 adaptivity. We're adapting the horizontal, and then down from each node of that adapted mesh in the horizontal, we put a different number of nodes. So we do 1D adaptivity down every column, and then join them up.
What if you had high order in the vertical?
Sorry?
If you had high order in the vertical, that would alleviate some of the problem?
It might alleviate it, but it wouldn't get rid of it though. So that's in the horizontal and vertical. So the nice thing here, if you notice, is if there was any spurious noise in this setup, this has been exaggerated by quite a lot in the vertical. If there's any spurious noise, you see it here. So even though this looks a little bit unattractive, well, the dynamics of doing are actually pretty robust to that. And I'm really running out of time, so I'm just going to skip and show you how we're extending that setup to, this is now fixed mesh, but it's realistic. It's forced by real atmospheric data. And I think the take-home message at the moment, this is very much work in progress, is that it's running stably and it's running in reasonable time, and that we can run this simulation for a year on our clusters in a week, let's say, which for us is reasonably quick. You can actually see some seasonal effects. You can see things spinning up. And this is really the approach I've been telling you about, the P1DG, P2 element pair, P1DG for temperatures and salinity. At the moment we're using something motivated by the NEMO layering, where we're putting the Z levels. At the moment this isn't adapting. And this same setup has been used on some, starting to get some interesting results out at global scales. This is currently still barotropic, but the formulation seems to be robust. So I'm going to finish. So things that I haven't told you about that I'd be happy to discuss offline are an extension of that renewables work is actually to start moving those little blobs, those turbines around using adjoint-based optimization, which I think is very exciting. We have a new project on coupled landslides. Remember at the start I showed you some landslides, a multiscale tsunami, and then inundation modelling. So when I was interested in adaptive tsunami modelling, I'd be interested to talk to them. Fluid structure interaction I haven't told you anything about, but again, these sort of moving more into the CFD scale, we can do a lot on the coastal engineering scale, or coupling coastal engineering scale to coastal and shelf seas. With the British Antarctic Survey, who are just down the road, we're working on sea ice and under ice shelf modelling. And I mentioned compressible flows, again I talk offline, and multi-phase flows. So this final slide. So I've demonstrated simulations using unstructured and anisotropic adaptive meshes. I think for me, robustness of the digitalization and flexibility you have over the mesh, the digitalization, the equations, code, physics, really is key. Well, unless you're trying to solve one specific problem and you know how to do it, these things are key. But still, and this has been the case for the last 10 or 20 years, the computational cost, and these days more so probably parallel scalability, is critical. We really need robust as well as accurate element choices and advection methods. I think I've shown you some slides motivating that. Things that I haven't discussed are how you parameterize subcomputer scale processes and how these parameterizations interact with varying resolution. So something like LES, Brits will take these into account, other parameterizations don't necessarily. And I think the most general that could be addressed here is we still don't really know where, when and how to most correctly adapt the mesh. I've showed you the results in the gravity current of adapting a different number of times, or having some fudges where you push the resolution ahead of where you need. So that's fine if you can spend time looking at a particular simulation, playing with how you're adapting the mesh, running something, trying to get out right. But if you come at something fresh, you don't know what's going on, we certainly need a much more of a black box type approach to give people a decent result. Otherwise you're going to get a bad result at a huge cost. So I think there's a lot of, with these approaches there's a lot you can do, but there's also a lot that you can mess up. So a more of a black box approach to as much of it as possible I think is important. So I'm going to stop there and apologise for overrunning.
Matt has gone crashing through even the additional time that he got from me finishing early, so I think I'm going to have to kick you off the stage. There were quite a lot of questions during the talk, and we're going to go to coffee in half an hour or so. So Those of you who wish to have another go at math then are more than welcome to. But we're now going to shift